Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the fifth class of chapter 6 on counting in the course CS131 Discrete Structures held at FCSE GIK Institute. I'm your course instructor, Dr. Raja Hashim Ali, and I'll be talking about the generalized combinations and permutations. So in the previous lectures, in chapter 6, what we've learned about is we have learned some of the basic rules that can be applied for counting. For example, the sum rule and the product rule. And then we have seen some important applications of the tree diagram and how that can be used to use for counting and enumerating. This was then followed by section 6.2, where we talked about the pigeonhole principle and the generalized pigeonhole principle. Then we basically discussed some of the important topics of maths, which is basically combinations and permutations. And this was then followed by some applications of combinations in binomial theorem and binomial expansion. In this particular lecture, in this particular section, we are going to be talking about section 6.5, which is a generalized combination permutation, which is going to build up on the concept of permutations and combinations and give a more generalized formula for them. So let's, without further ado, let's talk about the generalized combination permutations. What is permutation with repetition? So for example, let's say how many strings of length R can be formed from the uppercase letters of the English alphabet. In this case, the position of the alphabet matters. That's the first thing that you note. The other thing that you note is that the letters themselves can be repeated easily. So for example, if you select A in the first position, you can still select A for the second position. There's no one stopping you from repeating an alphabet. Hence here, it's going to be for each position. We already know this through the product rule, that this is basically, let's say in English you have 26 raised to power, 26 alphabets for the first one, 26 for the second, 26 for the third. By product rule, we say 26 raised to power R for length R. Right? And that's exactly the answer that we get for this. So this was easy, right? Let's go to the relatively difficult one. Or let's first give a theorem for it. The number of R permutations of a set of n objects with the repetitions allowed is n raised to power R. And we know this already. You can actually calculate it, put in the formula for permutation. And in generic, since the repetition is allowed, this is what you come up to, right? N raised to power R. What about combinations with repetitions? How many ways are there to select 4 pieces of fruit from a bowl containing apples, oranges, and pears if the order in which the pieces are selected does not matter? Only the type of fruit and not the individual piece matters, and there are at least 4 pieces of each type of fruit in the bowl. How do you solve that? The answer to that is actually, since we are supposed to select 4 pieces from 3 possible types, and the order of the pieces does not matter. So and there are at least 4 pieces of each type. So let's say 4 multiplied by 3, 12. From 12 pieces, you have to select 4 pieces. How many different ways are there to select 4 pieces? So you can basically select all 4 apples, all 4 pears, or all 4 oranges, or you can select a mix of them, right? The answer to this would be a combination of 12 and 4, right? So a combination of 12 and 4 is going to be this one. What's the generic formula? The generic formula for combinations with repetitions is C n plus R minus 1 R, right? You want to select R elements from C n plus R minus 1. And this is equivalent, of course, to C n plus R minus 1 and n minus 1. R combination from a set with n elements when repetition of elements is allowed. So that's the generic formula for combination with repetitions, as we have seen the same formula or similar formula for permutations with repetitions. So how many ways are there to select 5 bills from a cash box containing $1 bill, $2 bill, $5 bill, $10 bill, $20 bill, $50 bills, and $100 bills? Assume that the order in which the bills are chosen does not matter. The order does not matter, hence it's basically the combination. That the bills of each denominations are indistinguishable. Since the bills are just indistinguishable, hence, and there are at least 5 bills of each type. So this is a combination problem with repetition. And for that, you just need to apply the formula Cn minus r plus 1, right? So just apply the formula Cn plus r minus 1 r. And if you n plus r minus 1 r, you're basically going to go for n is basically, what is n here? N r is 5, n is 1, 2, 3, 4, 5, 6, 7, right? 7 plus 5 minus 1 gives you 11. So C11, and since r is 5, so C11, 5. This gives you your solution. Suppose that a cookie shop has 4 different kinds of cookies, so 4 different types, n is 4. How many different ways can 6 cookies be chosen? You want to choose 6, r is 6. Assume that the only type of the cookie and not the individual cookie or the order in which they are chosen matters. So only the type of cookie matters, neither the order nor the individual cookie themselves matter. So this is basically n is 6, n is 4, r is 6, 6 plus 4, 10, minus 1, 9, c, 9, 6 is your answer. Precisely. Let's talk more about another example. How many solutions does the equation x1 plus x2 plus x3 equal 11 have where x1, x2, and x3 are non-negative integers? This is a slightly tricky question. In this case, you have to choose 3 different elements. So n is 3, right? The total sum is 11. So r is 11. So 3 plus 11 minus 1 and 11. This is equal to 78. So this is C13, 11, and this comes out to be 78. Okay, so given any of these questions, the number of elements here is basically you want to choose an x1, you want to choose an x2, you want to choose an x3. All of these x1, x2, and x3 there are 3 options here. In total, there are 11 choices to be made. So n is 3, 11 is r, and then you just fit it into the formula. So even for equations, you can actually solve them using this. And this is something that you can come up with, you can verify on your own using putting in all the possible values. Start from zeros, ones, and so on. And you'll see that you'll actually have 78 different possible options to solve this equation. So if x1 plus x2 plus x3 is equal to 4, for example, then it is basically 3 plus 4 minus 1. So 3 plus 3, 6. C6, comma 4. 6, 4. C6, 4 is basically equal to 6 into 5 divided by 2. So it's 15 different options. And you can verify it on this particular equation. So with that, I think I need to summarize the permutation, combination, and repetition. The main problem here is not the formula. The formulas are really easy. So if repetition is not allowed, and these are simple R combinations or R permutations, then the formula is what we discussed in section 6.2, n factorial divided by n minus r factorial for R permutations, and n factorial divided by r factorial into n minus r factorial for R combinations. This formula will be given to you in the exam. So don't worry about the formula. You can find it anywhere. The main problem is to identify in the question whether the order matters. If the order matters, you always need to go for permutation. If the order does not matter, then you can go for combination. Remember this thing. The order always matters if you change the order of the 2 choices and it becomes to be a new value. So if the order remains, if by changing the order, if the new value is still the same as the old value, then the order is not mattering. Then it's a combination. It's a permutation versus combination. If you can clear that point out, the second point, if you're sure that, okay, this is combination. A combination is something where order does not matter. Permutation is something where order matters. That's the first thing. Second thing you need to look at is, is the repetition allowed? Let us suppose that it is a permutation and the repetition is not allowed. You're not supposed to repeat it. An element, if chosen once, you cannot choose it again. The formula simply is n factorial over n minus r whole factorial. Just apply this formula, get full marks for it. But if you identify for incorrectly that the repetition is allowed, then you'll apply the wrong formula, n raised to power r. Your answer will be incorrect, and some marks, not all, but some marks will be deducted for identifying the wrong formula. You get no marks for formula. The whole marks or everything is actually based on your choice of how you have identified the right question. So for example, if the order does not matter and there is no repetition, I think I'll go for R combination without repetition. which is n factorial over r factorial into n minus r whole factorial. If the order doesn't matter and there's repetition, I'll go for the R combination with repetition, which is n plus r minus 1 factorial divided by r factorial into n minus 1 factorial. So with that, I think we're done with chapter 6. I wish you all the best for the subsequent chapters. In the next chapter, I think I'll be talking about graphs. These lectures are uploaded on YouTube for your reference. They'll be there for as long as you want until the final exam. And even after that, I think I won't be taking them down or out from the YouTube. These 5 lectures basically constitute, or actually 6 lectures, including the introductory lecture that I gave. These 6 lectures actually constitute chapter 6. Counting, and these are the topics that we have discussed in a lot of detail. You can actually go to these section exercises. You can go to the examples that I did not discuss and those examples that I did discuss to see more about the type of questions you should be expecting in the exam. You can kind of see the sample questions in the book as well. And at the end of each exercise, each section, you've got excellent questions. So I hope you're able to learn something about counting from me in this course, and I hope that this helps you in your future courses as well, networks and other things, particularly where different complexity is involved. I think that's a topic that I'll discuss in this course as well as it will be discussed later on in design and analysis of algorithms, in the course of data structures, as well as whenever you use an algorithm, you'll always have a term complexity involved with it. And in complexity, of course, these combinations, permutations, pigeonhole principle, etc., are useful tools to apply and learn. The sum rule, the tree diagram, etc., is an extremely important topic. It's a very interesting topic, and I think these are very, very useful for you in your future courses as well, on future topics, the theoretical topics in particular in CS and CE and in AI, of course. So with that, I'd like to thank you all for listening to my lecture, and I hope to see you in the next lecture, which is going to be on chapter 10, graphs, and we'll formally begin that from the next lecture. Thank you, take care, and Allah Hafiz.